Look up tonight. The stars look close. They hang in the sky like lanterns strung across a garden, and every civilization that has ever existed has assumed they were the next destination after the planets. They are not. The distance between one star and the next is not simply larger than the distance between planets. It is a different kind of distance entirely. It is the distance where engines become pointless, where radio signals become whispers, where a rescue mission becomes a fantasy, and where the human lifespan becomes a cruel joke. It is the first distance in the universe that does not merely challenge exploration, it begins to break it. And the terrifying part is that this wall does not start at the far edge of the galaxy. It starts at the nearest star. If this is the kind of story that changes how you see the night sky, hit like and subscribe. We go where the questions actually lead. Are you comfortable? Let's begin. There is a trick the sky plays on you every single night of your life. You walk outside, you look up, and you see the stars. They are bright. They are everywhere. Some of them form patterns you learned as a child. And without thinking about it, without doing any math or consulting any chart, your brain does something automatic and deeply wrong. It places them nearby. Not close in the way your neighbor's house is close, but close in the way that matters for a species that has spent its entire history treating visible things as reachable things. If you can see a mountain, you can walk to it. If you can see an island from the shore, you can sail to it. If you can see the moon hanging above the trees, then surely, with enough cleverness and enough time, you can get to that too. And the thing is, that instinct was correct for every single destination humanity has ever pursued, until now. The history of human exploration is a story of distances that looked terrifying and then shrank. The Pacific Ocean seemed infinite to the first Polynesian navigators who pushed their canoes beyond the sight of land. It was not infinite. They crossed it. The Atlantic seemed like a wall between the known world and oblivion. Columbus crossed it in about 2 months. The distance between the Earth and the Moon seemed like the most ambitious leap any species could ever attempt. Apollo 8 crossed it in 3 days. Every time the distance grew, the tools grew to match it. Sails replaced paddles, steam replaced sails, rockets replaced everything, and with each leap, the fundamental relationship between a human being and a destination stayed the same. You could see where you were going. You could communicate with where you came from. You could carry enough supplies to survive the trip. And if something went wrong, there was at least a theoretical possibility that someone could come help you. That framework held for every journey in human history. It held across oceans, it held to the moon, and with some stretching, it holds for Mars. Mars is far. Make no mistake about that. At its closest approach, Mars sits roughly 54.6 million kilometers from Earth. At its farthest, the distance swells to over 400 million kilometers. A crewed mission to Mars, using current propulsion technology, would take somewhere between 6 and 9 months each way, depending on the trajectory and the alignment of the planets. That is a long time in a metal tube. It is a genuine hardship. But notice what does not break. A radio signal from Mars reaches Earth in somewhere between 3 and 22 minutes, depending on orbital positions. That means mission control can still talk to the crew. The delay is frustrating, but manageable. Supplies can be pre-positioned on the Martian surface by robotic landers sent ahead of the crew. If a medical emergency strikes, the crew is on their own for treatment, but a resupply mission could theoretically be launched from Earth and arrive within months. The mission fits inside a single human career. The astronauts who leave will be recognizable when they return. Their children will still be children. Their language will not have changed. Their civilization will still be there, largely the same as when they departed. Every one of those things matters. not because they are luxuries, but because they are the invisible scaffolding that makes the word mission mean something. A mission has a beginning and an end. It has a chain of command that reaches back to a home base. It has a reasonable expectation that the people who planned it will be alive to receive its results. Mars stretches this scaffolding. It bends it. It strains some of the joints, but the scaffolding holds. The mission is still a mission. Exploration is still exploration. The relationship between the traveler and home remains intact. It is worth pausing on this scaffolding because we have never had to think about it consciously. It has always just been there, so reliable and so automatic that it became invisible. Consider how much of it was present even during the most dangerous missions humanity has ever attempted. When Apollo 11 landed on the Moon in July of 1969, Neil Armstrong and Buzz Aldrin spent roughly 2.5 hours walking on the surface. The entire time, they were in voice contact with Mission Control in Houston. The delay was barely perceptible, a little more than a second each way. When Armstrong's heart rate spiked during the final descent because the onboard computer was throwing alarms and the landing site was strewn with boulders, Houston could hear the tension in real time. Charlie Duke, the capsule communicator, could respond within seconds. The decisions being made on the spacecraft and the decisions being made on the ground were woven together into a single, continuous thread of judgment. If something had gone catastrophically wrong on the surface, if the ascent engine had failed to ignite, if the cabin had depressurized, there was nothing Houston could have done to physically save them. But Houston would have known. The families would have known. The world would have known. The connection to home was unbroken, even in the worst possible scenario. The astronauts were never truly alone because information still flowed in both directions fast enough to carry the weight of shared experience. Now consider a crewed Mars mission, which every major space agency has spent decades studying. The communication delay changes the texture of the relationship between crew and ground, but it does not sever it. A crew on Mars would receive daily video messages from family. They would upload scientific data and receive analysis from teams on Earth within the hour. They would watch news broadcasts, follow cultural events, participate in interviews. The delay would make conversation awkward, but not impossible. A message sent in the morning would receive a reply by afternoon. The crew would experience seasons on Mars, roughly twice as long as Earth seasons, but recognizable. They would have sunrises and sunsets. They would walk outside, even if only in pressure suits. They would see a horizon. They would have weather, thin and cold but real. The psychological environment of a Mars mission is demanding, but it contains enough variety, enough novelty, enough connection to the rhythms of a natural world to keep the human mind engaged. More importantly, a Mars mission has a return date. Current mission architectures assume surface stays of roughly 500 days, followed by a return transit of 6 to 9 months. The entire mission, from launch to landing back on Earth, fits within roughly 3 years. The astronauts who depart will be recognizably themselves when they return. Their muscles will have weakened. Their bones will have thinned. They will carry an elevated lifetime cancer risk from radiation exposure. But they will return to the same civilization, the same families, the same institutions that sent them. They will be debriefed. They will write memoirs. Their grandchildren will ask them what it was like. The arc of the mission has a beginning, a middle, and an end, and the end brings the travelers home. This is exploration. This is what the word has meant for every generation that has used it. A departure, a journey, an arrival, a discovery, and a return. The return is not optional. It is constitutive. It is what distinguishes an expedition from a banishment. Even the most dangerous voyages of the Age of Sail, the ones from which significant numbers of crew did not return, were structured around the expectation of return. The ships were provisioned for a round trip. The crew signed on for a defined period. The investors expected an accounting. The knowledge gained was carried home in logbooks and charts and the memories of survivors. Exploration has always been a loop, a circle that begins and ends at the same point, enriched by what was gathered along the way. The distance between planets allows this loop to close. The distance between Mars and Earth is large enough to test every system and every person involved, but small enough that the loop still functions. The travelers leave, and they come back, and the civilization that sent them is still there when they arrive, and the knowledge they carry integrates into the culture that paid for the trip. The distance between stars does not allow this loop to close. It stretches the loop past the point where any part of it retains its original meaning. The departure happens, but the return may never come. The knowledge is gathered, but it may arrive at a civilization that has forgotten it, asked the question. The travelers leave as explorers and become, somewhere in the crossing, something else entirely. Not explorers, not colonists in the traditional sense, something for which we do not yet have a word, because no human being has ever occupied that category. Now, do something that sounds simple but is not. Look past Mars, look past Jupiter, past Saturn, past the ice giants lurking in the dim outer reaches of the solar system. Look past the Kuiper Belt, past the scattered disk of frozen remnants left over from the formation of the planets. Keep going, until the sun is just another star behind you. Keep going until you have traveled so far that the entire solar system, every planet, every moon, every asteroid, every comet, every piece of human-built hardware that has ever existed is a single dim point of light, lost among millions of others. You are now in interstellar space. And the nearest star system, the closest place where another sun burns and another set of worlds might orbit, is Alpha Centauri, sitting 4.37 light-years away. That number needs to be unpacked because it is one of those figures that sounds manageable until you convert it into something a human mind can actually process. 1 light-year is the distance that light travels in a single year. Light moves at roughly 300,000 kilometers per second. In 1 year, it covers approximately 9.46 trillion kilometers. Multiply that by 4.37, and the distance to Alpha Centauri comes out to approximately 41.3 trillion kilometers. 41 trillion. That is not a distance that any analogy can make feel intuitive, but the attempt is worth making because the failure of the analogy is itself the point. Imagine shrinking the solar system so that the distance between Earth and the Sun is 1 centimeter. At that scale, Mars would sit roughly 1.5 centimeters from the Sun. Jupiter would be about 5 centimeters out. Neptune, the outermost major planet, would be roughly 30 centimeters away. On a desk, you could fit the entire solar system within arm's reach. Now, at that same scale, where the Earth-Sun distance is 1 centimeter, Alpha Centauri would be approximately 2.8 kilometers away, not 2.8 centimeters, kilometers. You would need to leave your desk, walk out of the building, cross your neighborhood, pass through the commercial district, keep walking, and you still would not be there. The entire solar system from the Sun to Neptune fits on your desk. The nearest star is a 40-minute walk from your desk. That is the scale jump. That is what happens between interplanetary and interstellar. The gap is not a factor of 10 or a factor of 100. From Neptune's orbit to Alpha Centauri, the distance increases by a factor of roughly 9,000, and that is to the nearest star. Most stars are incomparably farther. Right now, as you listen to this, the farthest human-made object from Earth is Voyager I. It launched on September 5, 1977. It flew past Jupiter. It flew past Saturn. It took the most famous photograph in history, the pale blue dot image of Earth as a tiny speck suspended in a beam of light, and then it kept going. It crossed the termination shock in 2004. It entered interstellar space, the region beyond the influence of the solar wind, on August 25, 2012. It has been flying away from Earth for nearly 49 years. It travels at roughly 17 kilometers per second, which is approximately 61,000 kilometers per hour. That is fast. That is faster than any bullet, faster than any sound wave, faster than anything in your daily experience. Voyager 1 is, by any human standard, screaming through space, and it has barely moved. As of early 2026, Voyager 1 is approximately 172 astronomical units from Earth. An astronomical unit is the distance from the Earth to the Sun, so Voyager is roughly 172 times farther from us than the Sun. That sounds impressive, and it is. Later this year, Voyager 1 will reach a milestone that captures the scale problem perfectly. In November 2026, the spacecraft will become the first human-made object to travel one full light day from Earth. One light day is the distance light covers in 24 hours, approximately 25.9 billion kilometers. At that point, if Mission Control at the Jet Propulsion Laboratory sends a command to Voyager, the signal traveling at the speed of light will take 24 hours to arrive. The response will take another 24 hours to return. A simple good morning and reply will consume 2 full days. That is a meaningful milestone. It is worth celebrating. But now measure it against the destination. Alpha Centauri is 4.37 light-years away. A light-year contains 365 light days. 4.37 light-years is roughly 1,595 light days. Voyager 1, after nearly half a century of flight, has covered 1 light day. It would need to cover roughly 1,594 more to reach the nearest star system. At its current speed, that journey would take approximately 73,000 years. 73,000 years. Written out because that number deserves to be stared at. 73,000 years ago, anatomically modern humans were sharing Europe with Neanderthals. The last ice age had not yet reached its peak. Agriculture would not be invented for another 60,000 years. Every empire that has ever existed, every language spoken today, every city on Earth, every piece of technology, from the wheel to the semiconductor, was developed inside the window of time. It would take Voyager to reach the nearest star. If a Paleolithic hunter-gatherer had strapped a message to Voyager 1 at the moment it launched from Cape Canaveral and aimed it at Alpha Centauri, that message would not arrive for 730 centuries. The hunter-gatherer's entire genetic lineage would have risen, flourished, forgotten its own origins, and possibly gone extinct before the message completed its journey. That is not a travel time, that is a geological epoch, and this is the trap that the night sky sets for you. Because you look up and you see Alpha Centauri. If you are in the southern hemisphere, you can see it with your naked eyes. It is the 3rd brightest star system in the sky. It looks close. It looks like it is right there, just past the other bright ones, a short hop beyond the familiar. Your eyes and your instincts are lying to you. The light you see left Alpha Centauri 4.37 years ago. In the time since that light departed, you have lived through over 1,500 days, and every single one of those days, that light was traveling at 300,000 kilometers per second, the fastest speed anything in the universe is permitted to achieve. That is how far away it is. Not far in the way Mars is far. Not far in the way that makes an engineer frown and then start sketching a solution. Far in the way that makes the word far feel like it was invented for a smaller universe. Here is what makes this particular distance different from every other large distance in space. It is not simply that the number is big. Big numbers exist everywhere in astronomy. The observable universe is 93 billion light-years across. The Andromeda Galaxy is 2.5 million light-years away. Those distances are staggering, but they are also abstract. Nobody is planning a mission to Andromeda. Nobody is drawing up crew rosters for a trip to the edge of the observable universe. Those distances live safely in the category of things that are obviously impossible and therefore do not taunt us. The distance to the nearest star is different. It taunts. It sits in a cruel middle zone between the achievable and the impossible. It is close enough that we can see the destination, study it, name its planets, and measure its chemistry. It is close enough that physicists can sketch theoretical propulsion systems that could, in principle, cross it within a human lifetime. It is close enough that the Breakthrough Starshot project, announced in 2016 with $100 million in initial funding, proposed sending gram-scale probes to Alpha Centauri at 20% of the speed of light, arriving in roughly 20 years. The project made the cover of scientific journals. Stephen Hawking endorsed it. It felt, for a moment, like the gap might be closable. By 2025, the project was on indefinite hold. Scientific American reported that of the $100 million pledged, roughly $4.5 million had actually been spent across about 30 contracts. The technical challenges had not been overcome. They had not even been fully mapped. The laser array required to accelerate a gram-scale sail to 20% of light speed would need a combined coherent power output of up to 100 gigawatts, a figure that exceeds the total electrical generating capacity of many nations. The sail material would need to survive being illuminated by that beam without vaporizing. The tiny probe, a chip weighing roughly 1 gram, would need to carry cameras, sensors, a power source, and a communication laser capable of sending data back across 4.37 light-years, a distance so vast that even a laser signal would take over 4 years to return, and would arrive so faint that a receiving telescope, 30 meters across, would pick up only a few photons at a time. And even if all of that worked, the probe would not stop. It would tear through the Alpha Centauri system at 20% of the speed of light, roughly 60,000 kilometers per second, crossing the entire system in a matter of hours with no ability to orbit, land, or linger. It would be a bullet passing through a room, capturing a few blurred snapshots before vanishing into the void beyond. That was the most optimistic proposal serious scientists have ever put forward for reaching another star. It was the absolute lightest, fastest, cheapest version of the idea that anyone could design. And it stalled, not because of politics or funding alone. It stalled because the engineering required to send a chip, the weight of a paperclip, across the interstellar gulf at a fraction of light speed, remains beyond what humanity can currently build, test, or operate. Now hold that failure in your mind and consider what it would take to send not a chip but a human being. Not a gram, but tens of thousands of kilograms of habitat, food, water, oxygen, shielding, medical supplies, engines, and fuel. The energy requirements do not scale politely. They explode. To accelerate a spacecraft with a mass of even 100,000 kilograms to 10% of the speed of light, you would need an energy budget measured in hundreds of petajoules, the equivalent of thousands of nuclear warheads converted entirely into directed thrust with perfect efficiency. No propulsion system that exists or is under development comes within orders of magnitude of delivering that kind of energy in a controlled, sustained, survivable manner. Chemical rockets, the kind that carried Apollo to the moon and that still carry every crewed mission into orbit, produce exhaust velocities of roughly 4 to 5 kilometers per second. To reach 10% of the speed of light, you need 30,000 kilometers per second. The gap between what chemical rockets can achieve and what interstellar speeds demand is a factor of roughly 6,000. Ion engines, which are more efficient but produce tiny amounts of thrust, could in theory achieve higher velocities over long periods. But the time scales involved stretch into centuries, and the power requirements remain enormous. Nuclear pulse propulsion. The concept behind the 1950s-era Project Orion proposed detonating nuclear bombs behind a massive plate to push a spacecraft forward. The design was theoretically capable of reaching a few percent of light speed, but it required thousands of nuclear detonations, a spacecraft the size of a city block, and a political willingness to launch atomic weapons into space that has never existed and likely never will. Fusion propulsion remains theoretical. Antimatter propulsion remains in the domain of physics papers, not engineering blueprints. Every propulsion concept that could theoretically close the interstellar gap either does not exist yet, cannot be built at the required scale, or introduces problems as severe as the one it solves. This is not a situation where the answer is just around the corner, and we need a few more decades of research. This is a situation where the basic physics of the problem imposes constraints so severe that incremental progress does not visibly close the gap. The distance between the stars does not care how clever you are. It does not care how much funding you have. It does not reward ambition the way shorter distances do. It simply sits there, vast and patient, converting every plan into a set of numbers that do not work. And yet, the stars are right there. You can see them. Proxima Centauri, the closest individual star to the Sun, is a dim red dwarf sitting 4.24 light-years away. It has at least 2 confirmed planets. One of them, Proxima Centauri b, orbits within the habitable zone. It is roughly Earth mass. It was announced by the European Southern Observatory in August of 2016. Alpha Centauri A and B, the 2 sun-like stars at the center of the system, remain under active investigation for additional worlds. The system is not a single point of light. It is a neighborhood with 3 stars and a growing list of confirmed and candidate planets. The nearest stellar doorstep is not barren. It is furnished, decorated, and possibly habitable, and it sits across a gulf that no human technology can currently cross. There are worlds next door. The universe put destinations right beside us, close enough to study, close enough to name, close enough to make a person ache with the desire to visit them. And then it filled the space between here and there with 41 trillion kilometers of nothing. Not nothing in the way that a desert is nothing. Nothing in a deeper, colder, more absolute sense. No gas stations, no landmarks, no gravity wells to slingshot around, no sources of energy to harvest, no matter thick enough to scoop for fuel. Just vacuum, radiation, and time stretched beyond any meaning a human life can contain. The cruelest thing about the distance between stars is not that it is large. Large distances exist throughout the universe, and most of them are irrelevant to daily life. The cruelest thing is that it is the first distance that looks crossable but is not. It is the first distance that invites you to try and then punishes you with physics for accepting the invitation. It is close enough to dream about and far enough to break every dream it invites. The space between planets is a challenge. The space between stars is something else entirely. What exactly it is, what it does to communication, to energy, to hardware, to biology, to the very idea of a mission, is what comes next, and every layer of the answer is worse than the one before it. Every problem in space that humanity has ever solved shared one quiet advantage that nobody talks about. The problem existed within reach. When Apollo 13's oxygen tank exploded halfway to the moon, 3 men were stranded in a crippled spacecraft 200,000 miles from home. The situation was desperate. Engineers in Houston had to invent a carbon dioxide filter out of materials the crew had on board, improvise power management for a module that was never designed to sustain 3 people, and calculate a free return trajectory that would sling the spacecraft around the moon and back to Earth using almost no fuel. It was one of the most brilliant acts of emergency problem-solving in human history. And the entire thing was possible for one reason that rarely gets mentioned. The crew could talk to Houston. The communication delay between the moon and the Earth is roughly 1.3 seconds each way. A question from the astronauts reached Houston in just over a second. The answer came back in just over a second. The conversation was essentially real time. Engineers on the ground could hear the crew's breathing, sense the panic in their voices, watch the telemetry update in nearly continuous streams, and respond with instructions that arrived while the emergency was still unfolding. That link between the spacecraft and the ground, thin and fragile as it was, carried the weight of the entire rescue. Without it, the crew would have died. Now stretch that link to Mars. At closest approach, Mars is roughly 3 light minutes from Earth. At its farthest, it is over 22 light minutes away. A round-trip conversation takes between 6 and 44 minutes. That delay is already a serious challenge for crewed missions. If a medical emergency occurs on Mars, the crew sends a message describing the problem. Then they wait. 6 minutes at best, 22 minutes at worst, before mission control even hears their words. Then the experts on the ground discuss, consult, argue, and compose a response. They transmit it. Another 6 to 22 minutes pass. By the time the crew receives the first piece of advice, anywhere from 12 to 44 minutes have elapsed since they called for help. That is uncomfortable. It changes the nature of the relationship between crew and ground. It forces a Mars crew to be far more autonomous, far more self-reliant, far more trained in independent decision-making than any crew in the history of spaceflight. But the link still exists. The delay is measured in minutes. The conversation is slow but possible. A complex problem can be worked through in a series of exchanges over the course of hours or days. Mars is hard, but the thread connecting the travelers to home is still intact. At Alpha Centauri, that thread snaps. A radio signal or a laser pulse traveling from Earth to the Alpha Centauri system at the speed of light takes 4 years and 4 months to arrive. The return signal takes the same. A single round-trip exchange, 1 question and 1 answer, consumes 8 years and 8 months. Think about what that means in operational terms. If a spacecraft in orbit around Proxima Centauri sends a message saying the navigation system has failed, the people on Earth who receive that message will not hear it until 4 years and 4 months after it was sent. They will compose a response, a set of diagnostic procedures, a software patch, an alternative navigation protocol. They will transmit it. The crew will receive it 4 years and 4 months later. By the time the crew opens the reply to their distress call, 8.5 years will have passed since the original failure. Whatever crisis prompted the message will have been resolved by the crew on their own, or it will have killed them long before help arrives. This is not a communication delay. It is the end of communication in any meaningful operational sense. There is no mission control for an interstellar crew. There is no Houston to call. There is no team of experts sitting in a room with headsets, watching screens, ready to jump in with a solution at a critical moment. All of that vanishes completely The moment a spacecraft crosses the threshold from interplanetary to interstellar distance, the crew is alone. Not alone in the poetic sense that astronauts on the space station sometimes describe when they look down at Earth from orbit and feel small. Alone in the absolute, structural, irreversible sense that no human voice from home will reach them in time to matter for any decision they will ever make again. Every emergency protocol in the history of spaceflight assumes that the ground can participate. Every medical procedure developed for space assumes that a flight surgeon on Earth can be consulted. Every software update, every trajectory correction, every judgment call about whether to abort or continue has always involved someone at home who could weigh in. On an interstellar mission, all of that institutional knowledge, all of that collective expertise is reduced to whatever the crew brought with them in their heads and in their onboard computers when they left. The rest of civilization becomes a memory that sends letters with an 8-year delivery time. And communication is only the first system that collapses. The next is energy. The energy required to move a meaningful payload across interstellar distances is not merely large. It exists in a category that has no precedent in human engineering. To understand why, you need to understand something about the relationship between speed, mass, and the fuel required to connect them. In rocketry, there is a number called the delta V budget. It represents the total change in velocity a spacecraft needs to achieve its mission. For a trip to low Earth orbit, the delta V budget is roughly 9.5 kilometers per second. For a trip to Mars, it is in the range of 4 to 6 kilometers per second beyond low Earth orbit, depending on trajectory. For a trip to Alpha Centauri at 10% of the speed of light, the delta V budget is 30,000 kilometers per second. That is not a gentle increase. It is a leap across 3 orders of magnitude from the most ambitious mission ever attempted. The tyranny of the rocket equation makes this exponentially worse. Every kilogram of fuel you add to the spacecraft increases its mass, which means you need more fuel to accelerate that additional mass, which increases the total mass further, which requires still more fuel. The relationship is logarithmic and vicious. For chemical propulsion, achieving a delta V of 30,000 kilometers per second would require a fuel-to-payload ratio so astronomical that the spacecraft would need to be almost entirely fuel, with the actual payload, the habitat, the crew, the supplies, the scientific instruments, reduced to a vanishingly small fraction of the total mass. The numbers do not just fail to close. They fail so spectacularly that no serious engineer has ever proposed chemical rockets for interstellar travel. They were never candidates. They are eliminated by arithmetic before the design phase even begins. More advanced propulsion concepts improve the ratio but do not escape the fundamental problem. A fusion-powered spacecraft, if one could be built, would achieve higher exhaust velocities and therefore require less fuel per unit of delta V. But even optimistic fusion designs still require fuel masses measured in thousands of tons for a crewed interstellar mission. That fuel must be carried from the beginning, which means the spacecraft must be enormous at departure, which means the energy required to start the journey is enormous. Some proposals attempt to sidestep this by collecting fuel along the way. The Bussard ramjet, proposed in 1960, imagined scooping interstellar hydrogen with a magnetic field hundreds of kilometers wide and feeding it into a fusion reactor. The concept was elegant. The physics turned out to be uncooperative. Interstellar hydrogen is so sparse, roughly 1 atom per cubic centimeter, that the drag created by the magnetic scoop at high velocities would exceed the thrust generated by the fusion reactor. The ramjet would slow itself down faster than it could speed itself up. It was a beautiful idea that the interstellar medium quietly vetoed. The energy problem is not just about getting up to speed, it is also about stopping. A spacecraft that accelerates to 10% of the speed of light must decelerate by the same amount before it arrives, unless the mission plan is a flyby with no intention of entering orbit or landing. Deceleration requires carrying roughly the same amount of fuel as acceleration, which effectively doubles the fuel budget. A spacecraft that needs 1,000 tons of fuel to reach cruising speed needs another 1,000 tons to stop at the destination. That second 1,000 tons must also be accelerated from Earth, which means the initial fuel load must be even larger to account for it. The compounding is relentless. Every stage of the journey multiplies the demands of every other stage. Before we move beyond the energy problem, it is worth making these figures tangible, because numbers measured in petajoules tend to slide off the surface of the mind without leaving a mark. The total energy consumed by the entire United States in a single year, every power plant, every vehicle, every factory, every light bulb and phone charger and server farm, is roughly 100 exajoules. That is 100 billion joules. To accelerate a modest crewed spacecraft, say 100,000 kilograms, to 10% of the speed of light would require on the order of 45,000 petajoules, or roughly 45 exajoules. That is not a small fraction of national energy consumption. It is nearly half of everything the United States produces in an entire year, every source combined, poured into a single object. And the comparison is still misleading, because the energy consumed by the United States in a year is spread across an entire continental infrastructure operating continuously for 12 months. The energy needed for the spacecraft must be delivered to a single object in a specific form through a specific mechanism in a controlled sequence within a finite acceleration window. There is no existing system capable of doing this. The energy output of the largest nuclear power plant on Earth, sustained at maximum capacity for over a century, would approximate the energy budget needed to accelerate this single ship to 1/10 of the speed of light. And that is just acceleration. Deceleration doubles it. The spacecraft needs more than 2 centuries of total output from the largest power plant ever built, delivered not as electricity to a grid, but as directed momentum to a hull. No engine currently under serious development can convert stored energy into thrust at the efficiency required. Fusion propulsion, the most promising candidate, has not yet achieved sustained net energy gain in a laboratory reactor, let alone in a compact, flight-rated engine capable of operating continuously for months or years. The International ITER fusion experiment in France, the largest and most expensive scientific instrument ever constructed, is designed to demonstrate that a fusion reaction can produce more energy than it consumes. It is not designed to produce thrust. It is not designed to be portable. It weighs approximately 23,000 metric tons. The gap between a stationary experimental reactor and a flight-ready fusion engine for interstellar propulsion is not a gap that a few engineering cycles will close. It is a gap measured in fundamental breakthroughs that have not yet occurred. There is another dimension to the energy problem that receives little public attention but dominates the internal discussions of mission designers. It is the problem of navigation. Within the solar system, navigation is difficult but well understood. Spacecraft use a combination of onboard star trackers, ground-based radar ranging, and the known gravitational fields of planets and moons to determine their position and trajectory. Deep Space Network antennas on Earth can track a spacecraft's position to within a few kilometers at the distance of Pluto. Course corrections are transmitted from the ground and executed by the spacecraft's thrusters. The entire process depends on 2 things: a detailed gravitational model of the environment, and a communication link fast enough to permit ground-based participation in navigation decisions. In interstellar space, both of those supports vanish. The gravitational environment between stars is effectively flat. There are no planets to use as reference points, no moons to swing around, no gravitational landmarks of any kind. The spacecraft is moving through a featureless void where the only reference points are the stars themselves, which shift their apparent positions so slowly across decades of travel that extracting precise positional information from them requires instruments of extraordinary sensitivity and stability. Onboard star trackers can determine orientation, which direction the spacecraft is pointing, but determining position, where the spacecraft actually is in three-dimensional space relative to its departure point and its destination, is a far harder problem when there are no nearby objects to triangulate against. Ground-based navigation support, the kind that has guided every deep space mission in history, is functionally absent. A course correction command sent from Earth to a spacecraft halfway to Alpha Centauri would take over 2 years to arrive. By the time the command is received, the spacecraft's position has changed by billions of kilometers. The correction is stale before it arrives. Real-time navigation from the ground is impossible. The spacecraft must navigate itself using onboard instruments and onboard computation for the entire duration of the crossing. The targeting problem makes this worse. Alpha Centauri is not stationary. The star system moves relative to the Sun at a total velocity of roughly 32 kilometers per second, combining its approach toward us and its lateral drift across the sky. Over a transit time of 43 years at 10% of the speed of light, Alpha Centauri will have shifted approximately 43 billion kilometers from where it appeared when the spacecraft launched. The spacecraft is not aiming at where Alpha Centauri is. It is aiming at where Alpha Centauri will be in 43 years. The calculation is straightforward in principle. Stellar proper motions are well measured, but the execution requires that the spacecraft maintain its trajectory with extraordinary precision across decades of flight. Without ground-based verification, through an environment where perturbations from the galactic gravitational field, the solar gravitational field, and the gravitational fields of unseen objects along the flight path can introduce errors that accumulate silently over years. A navigational error of a fraction of a degree at departure, uncorrected for 43 years, translates into a missed distance measured in billions of kilometers at arrival. The spacecraft would sail past its target star and continue into the void, unable to stop, unable to turn around, its fuel spent, its mission failed, its crew or its instruments lost to an emptiness that extends for light years in every direction. There is no second chance. There is no traffic control to call for guidance. There is no landmark to recognize and correct against. The spacecraft either hits its target or it misses, and the margin between those outcomes is defined by the precision of instruments that must function without calibration or replacement for half a century. Now add the distance itself, not as an abstract number, but as a physical environment that the spacecraft must survive while crossing it. Interstellar space is not empty. It is close to empty, far emptier than any vacuum achievable in a laboratory on Earth, but it contains enough material to matter at high velocity. The interstellar medium consists primarily of hydrogen atoms, roughly 1 per cubic centimeter, along with traces of helium and tiny grains of cosmic dust. At low speeds, this material is negligible. At 10% of the speed of light, 30,000 kilometers per second, each hydrogen atom strikes the forward surface of the spacecraft with the energy of a high-energy particle in a physics experiment. At that velocity, the kinetic energy of a single hydrogen atom upon impact is roughly 5 mega-electron volts. That is comparable to the energy of alpha particles produced in radioactive decay. The spacecraft's forward hull would be subjected to a continuous bombardment of these impacts, each one depositing energy into the shielding material. Over a journey lasting decades, the cumulative radiation dose from interstellar hydrogen alone would be substantial. Add to that the cosmic ray background, the high-energy protons and heavier nuclei that permeate the galaxy with energies ranging from millions to trillions of electron volts, and the radiation environment inside an interstellar spacecraft becomes one of the most hostile, sustained exposure scenarios ever contemplated. On the International Space Station, astronauts receive a radiation dose of roughly 150 millisieverts per year, about half from trapped particles in Earth's magnetic field and half from cosmic rays. The station orbits within the magnetosphere, which provides significant shielding. A spacecraft in interstellar space has no magnetosphere. It has whatever shielding it carries with it. Current estimates suggest that a crew traveling at a significant fraction of light speed through the interstellar medium would require shielding equivalent to several meters of water or dense polymer to reduce the radiation dose to levels compatible with long-term survival. That shielding adds mass. That mass increases fuel requirements. The fuel increase requires more energy. The spiral tightens. And there is a category of damage that shielding alone cannot prevent. Galactic cosmic rays, the highest energy particles in the natural universe, can penetrate virtually any practical amount of shielding. These are not gentle particles. A single cosmic ray nucleus, traveling at close to the speed of light, can strike a molecule of DNA inside a cell and shatter it, creating a track of ionization damage along its path. On Earth, the atmosphere and the magnetic field absorb the vast majority of these particles before they reach the surface. In deep space, they arrive unimpeded. Over a multi-decade journey, the crew's cumulative exposure to galactic cosmic rays would significantly elevate the risk of cancer, cardiovascular disease, cataracts, and central nervous system damage. NASA's current permissible career exposure limits for astronauts would be exceeded within the first few years of an interstellar transit, and those limits were designed for missions lasting months, not decades. This is where the interstellar distance problem begins to reveal its true architecture. It is not a single obstacle. It is a web of constraints where every thread connects to every other thread, and pulling on one tightens all the rest. You need speed to reduce transit time. Speed requires energy. Energy requires fuel. Fuel adds mass. Mass requires more energy. Speed creates radiation exposure. Radiation requires shielding. Shielding adds mass. Mass requires more fuel. More fuel requires a larger spacecraft. A larger spacecraft requires a more powerful propulsion system. A more powerful propulsion system requires more energy. And threading through all of it, invisible but absolute, is the distance itself, which determines how long every one of these conditions must be endured. Now, add time. Not time as an abstraction, but time as a physical force acting on the machine. Every component of a spacecraft has a design, lifetime. Electronics degrade from radiation damage and thermal cycling. Seals dry out and crack. Lubricants evaporate in vacuum. Bearings wear. Solder joints develop whisker-like metal filaments that can short-circuit connections. These are not speculative failure modes. They are well-documented degradation mechanisms that affect every piece of hardware ever operated in space. The International Space Station has been continuously occupied since the year 2000, and it requires constant maintenance. Astronauts spend a significant portion of their working hours repairing, replacing, and servicing equipment. Resupply missions from Earth deliver spare parts, tools, and replacement units on a regular schedule. The station functions because it is close enough to Earth to be maintained. An interstellar spacecraft cannot be maintained from Earth. Every spare part it will ever need must be on board when it departs. Every tool, every backup system, every redundant component must be carried from the beginning because there is nowhere to stop and no one to call. The reliability requirements for such a mission are unlike anything in the history of engineering. A crude interstellar spacecraft operating at 10% of the speed of light would need roughly 43 years to reach Alpha Centauri. Including acceleration and deceleration phases, the total mission duration could easily exceed 50 years. That means every critical system on the spacecraft must function without resupply, without external repair, and without replacement for half a century. No human machine has ever done this. Voyager 1 has operated for nearly 49 years, which is extraordinary. But Voyager is a robotic probe with no life support requirements, no crew to protect, and a steadily declining set of functional instruments. As of 2026, only 2 of its original 11 science instruments remain operational. Its radioisotope thermoelectric generators produce less power with each passing year as the plutonium-238 fuel decays. The spacecraft is functional in the sense that it still returns data, but it has been systematically shutting down systems for years to conserve dwindling power. It is a machine in managed decline. That is acceptable for a robotic mission whose scientific return diminishes gracefully as capabilities are lost. It is not acceptable for a vessel carrying human lives. A crewed spacecraft cannot shut down its life support system to save power. It cannot turn off its radiation shielding. It cannot reduce its atmospheric recycling to conserve energy. Every critical system must work fully and continuously for the entire duration of the journey, and the duration is measured in decades. There is a physical challenge woven through all of this that rarely appears in public discussions of interstellar travel, but dominates the engineering literature. It is heat. Not the heat of a star or the heat of atmospheric re-entry, but the slow, relentless problem of managing thermal energy inside a vessel surrounded by a near-perfect vacuum at 2.7 Kelvin. A spacecraft generates heat. Every electronic system, every life support process, every watt of power consumed by lighting, computation, air circulation, and water recycling produces waste heat. On the International Space Station, this heat is managed by an active thermal control system that circulates ammonia through radiator panels mounted on the station's truss structure. The panels radiate excess heat into space as infrared energy. The system works because the station's thermal budget is well understood, the heat loads are relatively modest, and the radiators can be sized appropriately for the task. An interstellar spacecraft carrying a crew for decades faces a thermal problem of a different magnitude. The internal heat load is continuous and substantial. The only mechanism for rejecting heat in a vacuum is radiation, because there is no air and no water outside the hull to carry heat away through convection or conduction. Radiative cooling is governed by the Stefan-Boltzmann law, which means the rate of heat rejection depends on the surface area and the temperature of the radiator panels. To reject the waste heat of a crude habitat operating for 50 years, the radiator surfaces must be enormous, adding structural mass, mechanical complexity, and additional points of failure to a spacecraft already burdened beyond any historical precedent. If the radiators are damaged by microparticle impacts, and over decades of flight through the interstellar medium such impacts are statistically inevitable, the spacecraft's ability to shed heat degrades. Internal temperatures rise. Electronics overheat. Life support systems lose efficiency. The failure mode is not dramatic. It is a slow thermal suffocation, the interior of the vessel growing incrementally warmer year after year as the radiators accumulate damage that cannot be fully repaired. until the margin between habitable and uninhabitable quietly disappears. Consider what 50 years of continuous operation means for the human systems aboard. The air recycling system must process the atmosphere without interruption for 50 years. The water purification system must function for 50 years. The food production or preservation system must provide adequate nutrition for 50 years. The thermal regulation system, which manages the enormous temperature differentials between the sunlit and shadowed surfaces of a spacecraft in the void, must maintain habitable conditions for 50 years. The structural integrity of the hull, subjected to continuous microparticle bombardment, radiation degradation, and thermal stress, must hold for 50 years. If any one of these systems fails catastrophically and the crew cannot repair it with onboard resources, everyone dies and no one is coming to help. The nearest help is 4 light-years away, and even if a rescue mission were launched the instant the distress signal arrived on Earth, it would take at minimum another 43 years to reach the stricken vessel. The crew that sent the distress call would have been dead for decades before the rescuers even departed. This is what the distance between stars does to the concept of rescue. It eliminates it. Not practically, the way that rescue is difficult in Antarctica or at the bottom of the ocean. Absolutely. There is no rescue capability between star systems. There is no Coast Guard. There is no emergency frequency that connects to someone who can come get you. The closest parallel in human experience might be the earliest deep ocean voyages, where ships that sank in mid-crossing simply vanished and were never found. But even those sailors were on the same planet as their families. The water they sank into was the same water that touched the shores of home. An interstellar crew that suffers a fatal systems failure dies in a void so remote that their wreckage will drift for millions of years without encountering another object of any kind. There is one more dimension of the problem that tends to receive less attention than propulsion and shielding, but may ultimately matter more. It is the question of what the crew does while crossing the Gulf. 50 years of transit means 50 years of daily existence inside a closed environment. 50 years of eating the same categories of food, breathing the same recycled air, looking at the same walls, seeing the same faces. Submarine crews experience psychological stress after deployments measured in months. Antarctic winter-over teams, isolated for periods of roughly 8 months, report elevated rates of depression, interpersonal conflict, and cognitive decline. An interstellar transit would last orders of magnitude longer, with no possibility of early return, no possibility of fresh personnel, no possibility of opening a window and breathing outside air. The psychological literature on long-duration isolation suggests that crews in confined environments undergo predictable phases of adjustment, an initial period of excitement, a gradual onset of monotony and frustration, a critical period of peak conflict and emotional distress, and either a resolution into functional routine or a breakdown into dysfunction. These phases have been observed in every isolated crew environment ever studied, from submarines to space stations to polar research bases. The critical difference is that in all of those environments, the isolation has a known endpoint. The submarine will surface, the winter will end, the space station crew will rotate. That endpoint provides a psychological anchor, a fixed point in the future that the mind can grip when the present becomes intolerable. An interstellar crew has no such anchor for most of the journey. The destination is decades away. Home is already unreachable. The endpoint is so far in the future that it loses its motivational power. Psychologists call this temporal discounting, the tendency for future rewards to feel less real and less motivating the farther away they are. A reward 50 years in the future has almost no motivational weight for a human mind. The crew, must sustain purpose, discipline, social cohesion, and mental health across a span of time that exceeds the design limits of human psychology, and they must do it without any of the external supports that normally sustain people through difficulty. No new relationships, no new environments, no news from home that arrives in less than 4 years. No shared cultural events, no sports seasons, no elections, no seasons of any kind. Just the hum of the recyclers and the slow scroll of stars through the observation port, unchanging, year after decade after decade. And all of this, every one of these constraints, applies to the most optimistic version of the scenario. 10% of light speed, 43 years of transit, a functional propulsion system, adequate shielding, reliable hardware, a psychologically stable crew. If any of those assumptions is relaxed, if the speed is lower, if the shielding is insufficient, if a critical system fails in year 12, the picture does not degrade gently, it collapses. The web of constraints that holds the mission together has no slack in it. Every margin is already consumed. Every buffer is already spent. There is no room for the kind of error that every other human mission has eventually encountered and survived because home was close enough to help. The distance between stars does not present a problem. It presents a system of problems wired together so tightly that solving one frequently makes another worse. More speed means more radiation. More shielding means more mass. More mass means more fuel. More fuel means a longer acceleration phase. A longer acceleration phase means more time exposed to the very conditions you were trying to reduce by going faster. The system resists optimization. It resists clever engineering. It resists the kind of incremental progress that carried humanity from canoes to aircraft carriers, because each incremental step in interstellar mission design runs into a wall imposed by the next constraint in the chain. This is what makes interstellar distance cruel in a way that no other distance is. It is not merely large, it is architecturally hostile. The gulf between one star and the next is not an empty stretch of road that a better car could cross. It is a web of compounding physical constraints that interact with each other in ways that resist every approach humanity has ever devised for overcoming distance. The distance does not just separate you from the destination, it attacks the mission from every direction at once, degrading communication, exhausting energy, eroding hardware, irradiating crew, and dissolving the psychological bonds that hold a human community together. And all of that is before you consider what happens when you arrive, because the nearest star system is not merely far away. It is a place with its own hostilities, its own indifference to human survival, and its own set of conditions that compound the punishment of the journey that brought you there. What waits at the other end of the cruelest distance in space is the subject of what comes next. Suppose you solve the engine. Suppose some generation of engineers, working with physics we have not yet discovered or materials we have not yet synthesized, builds a propulsion system capable of accelerating a crewed vessel to a significant fraction of the speed of light. Suppose they solve the fuel problem, the shielding problem, the reliability problem. Suppose the spacecraft departs Earth orbit under power, accelerates smoothly, and reaches cruising velocity. The interstellar gulf still has another weapon, and it is the one that no amount of engineering can fully deflect: time. Not time as a measure of distance remaining, but time as a corrosive force acting on the biological, social, and institutional fabric of the mission itself. The distance between stars does not merely test technology, it tests whether a group of human beings can remain a functioning society long enough to reach the other side. Every crewed space mission in history has relied on a structure that extends far beyond the spacecraft. The astronauts aboard the International Space Station are supported by a network of thousands of engineers, scientists, flight controllers, medical professionals, logistics specialists, and administrators spread across multiple countries. That network trains the crew, monitors their health, manages their schedules, resolves conflicts, repairs systems remotely, rotates personnel, and provides a psychological lifeline to the world outside the hull. The crew is never truly alone because the institution that sent them is always present, separated by only a few hundred kilometers and a signal delay measured in fractions of a second. Remove that institution. Remove the network. Remove the ability to rotate crew, consult specialists, or receive a familiar voice in real time. What remains is not a space mission in any sense that the word has ever carried. What remains is a small, closed society hurtling through a void with no external contact, no institutional support, no reinforcements, and no possibility of return. The question is whether such a society can survive itself for the duration of the crossing. The history of isolated human communities is not encouraging. The closest analogues we have are not space missions, but colonial expeditions, remote settlements, and intentional communities that attempted to sustain themselves in isolation for extended periods. The pattern that emerges from these examples is consistent and grim. Small, closed populations under sustained stress tend to fragment. Authority structures erode or become authoritarian. Interpersonal conflicts that in a larger society would be absorbed or diffused become existential crises when the group cannot expand, when no one can leave, and when the same individuals must coexist in close quarters indefinitely. The biosphere. Two experiment in the early 1990s sealed 8 people inside a closed ecological facility in the Arizona desert for 2 years. Within months, the group had fractured into rival factions, oxygen levels dropped, crops underperformed, morale collapsed. The experiment failed on almost every metric, and it lasted only 2 years in a structure located on Earth, surrounded by a civilization that could intervene at any moment. An interstellar crew would face the same pressures for 25 times longer, with no civilization within reach to intervene. Generational missions, proposals in which the crew that departs is not the crew that arrives, introduce an additional set of difficulties that compound the social ones. If the transit takes a century or more, the original crew will die on board. Their children will be born, raised, educated, and socialized entirely within the spacecraft. Those children will have no memory of Earth. They will have no personal connection to the mission's origin. They will not have chosen to be on the ship. They will have been born into a journey that their grandparents started, and they will be expected to maintain the systems, the discipline, and the purpose of a mission they never volunteered for. The ethical implications of this arrangement are profound and unresolved. You are asking people who had no say in their circumstances to dedicate their entire lives to a project conceived by ancestors they never met, in service of a destination they have never seen, with no option to decline. Every generation born on the ship inherits a set of obligations it did not choose and cannot escape. And the biological pressures on those generations are not abstract. They are grounded in population genetics, and they are severe. A viable breeding population, one capable of sustaining genetic diversity over multiple generations without dangerous levels of inbreeding, requires a minimum effective population size. Estimates vary depending on the assumptions used, but most geneticists place the lower bound for a self-sustaining population somewhere between 160 and several thousand individuals. Below that threshold, inbreeding depression accumulates over generations, increasing the frequency of recessive genetic disorders, reducing immune system diversity, lowering fertility, and gradually degrading the health of the population. A spacecraft carrying 100 people, already a staggering engineering challenge, would be below the minimum viable population for long-term genetic health. A spacecraft carrying several thousand people is not a vessel. It is a small city, and the mass, volume, energy, and life support requirements of a small city traveling at a fraction of the speed of light exceed anything that engineering has ever seriously proposed. Layer onto this the physiological effects of the space environment itself, sustained over decades or lifetimes. In microgravity, the human body deteriorates in well-documented ways. Bone density decreases at a rate of roughly 1 to 2% per month. Muscle mass declines, cardiovascular fitness drops. Intracranial pressure increases, leading to vision impairment in a significant percentage of long-duration astronauts, a condition now formally designated as spaceflight-associated neuroocular syndrome. The fluid shift toward the head in microgravity alters kidney function, immune response, and even gene expression. Astronauts who spend 6 months on the space station return to Earth measurably changed, and they recover only because Earth's gravity provides the loading their bodies need to rebuild. A centrifuge or rotating habitat section could in principle provide artificial gravity during an interstellar transit, but it adds mass, mechanical complexity, and points of failure to an already overburdened design. The bearings of a rotating section must spin continuously for decades without maintenance or replacement. The seal between the rotating and non-rotating sections must remain airtight for the entire duration. Any imbalance in the rotating section creates vibrations that propagate through the spacecraft structure and stress every component connected to it. The engineering is feasible in concept but punishing in practice, and every kilogram devoted to the centrifuge is a kilogram taken from shielding, from food production, from spare parts, from every other system competing for the same finite mass budget. Then there is radiation, which does not merely present an acute risk during the transit, but a chronic, cumulative, multi-generational one. The cosmic ray environment of interstellar space is inescapable. High-energy particles penetrate every practical thickness of passive shielding. The damage they inflict on DNA is not limited to the individual exposed. It includes damage to reproductive cells, which means mutations can be passed to subsequent generations. A population living in a chronic high-radiation environment for multiple generations would accumulate genetic damage at a rate significantly higher than a population on Earth, even with the best shielding that engineering can provide. The long-term consequence is an elevated mutation load across the population, increasing the frequency of developmental abnormalities, cancer predisposition, and reproductive failure. The crew that arrives at the destination, if a generational ship ever reaches one, would be genetically different from the crew that departed, not by choice or adaptation, but by accumulated damage. There is another biological clock ticking alongside the genetic one, and it is more immediate and more personal. It is the aging of the individual crew members themselves. The propulsion scenarios discussed most seriously in the scientific literature do not achieve 10% of the speed of light. They achieve lower fractions, 1% or 2% or 5%, because the energy requirements scale with the square of the velocity, and each increment demands exponentially more fuel. At 1% of the speed of light, roughly 3,000 kilometers per second, the transit to Alpha Centauri takes approximately 437 years. That is a generational ship by any definition, with all the problems we have already described. At 5%, the transit takes roughly 87 years. That is not a generational ship in the traditional sense, but it exceeds the lifespan of nearly every human who has ever lived. A crew that departs at age 30 arrives at age 117. They do not arrive, they die en route, and their children or their caretakers manage the arrival. Even at the more ambitious 10% of light speed, the transit takes 43 years. A crew that departs at age 35 arrives at age 78. They arrive as elderly people, assuming they survive the cumulative radiation exposure, the bone density loss, the cardiovascular deconditioning, and the decades of psychological stress. They step off the spacecraft, if there is a surface to step onto, as people at the end of their physical capabilities, tasked with the most demanding, pioneering challenge in human history, building the infrastructure for survival on an alien world. This is not a minor contradiction. It is a structural mismatch between the demands of the destination and the condition of the people who arrive there. The fittest, most capable, most adaptable version of the crew existed on the day they departed. Every year of transit degrades them. The distance between stars does not merely consume time. It consumes the youth and the capacity of the people who attempt to cross it, delivering them to the destination as diminished versions of who they were when they started. Some proposals attempt to address this through suspended animation or cryogenic preservation, placing the crew in a state of biological stasis for the duration of the transit and reviving them upon arrival. This is an elegant concept and a staple of science fiction, but it does not currently exist as a medical technology. No human being has ever been placed in cryogenic suspension and successfully revived. The challenges are fundamental. Human cells contain water, and when water freezes, it forms ice crystals that puncture cell membranes, destroying tissue. Vitrification, the process of cooling tissue so rapidly that ice crystals do not have time to form, has been demonstrated on small tissue samples and individual organs in laboratory settings, but never on a complete human body. The revival process, even if freezing damage could be prevented, would require restoring function to every organ system simultaneously, a coordination problem of staggering complexity. Cryonics remains in the domain of hope and speculation, not proven capability, and projecting it as a solution to the interstellar transit problem amounts to assuming a medical breakthrough of a kind that has no precedent and no guaranteed timeline. The biological reality is that the human body was designed by evolution for a lifespan of roughly 70 to 80 years, and for an environment that includes gravity, atmospheric pressure, magnetic shielding, and a radiation dose rate orders of magnitude lower than what interstellar space provides. Every aspect of human physiology is optimized for conditions that do not exist between the stars. The interstellar environment is not merely inhospitable to human biology. It is adversarial in ways that accumulate over time, degrading every system in the body simultaneously, from the macroscopic level of muscle and bone down to the molecular level of DNA repair mechanisms. And here is the compounding element that makes the destination problem even more punishing. Alpha Centauri is the nearest star system. It receives the most attention because it costs the least to reach, in the same way that the nearest island receives the most attention from a castaway scanning the horizon. But what lies beyond it? The next nearest star is Barnard's star, a dim red dwarf sitting roughly 5.96 light-years from Earth. After that comes Wolf, 359 at 7.86 light-years, then Lalande, 21185 at 8.31 light-years. Each step outward increases the transit time, the energy budget, the radiation exposure, and every other cost we have catalogued. The distances do not plateau, they continue to grow, and the stars at those distances are overwhelmingly red dwarfs, small, cool, and prone to the same flare activity that threatens the habitability of Proxima Centauri b. The handful of sun-like stars in the solar neighborhood are farther still. The idea that Alpha Centauri might be inhospitable and that we could simply try the next star over misunderstands the scale. The next star over is another 50% farther away, which means another 50% more fuel, another 50% more transit time, another 50% more radiation exposure, another 50% more hardware degradation. The costs do not add, they multiply. Each additional light-year compounds every problem in the chain, and the chain is already strained to breaking at 4.37. The solar neighborhood is not a dense cluster of convenient destinations separated by manageable gaps. It is a scattering of dim, often hostile stars separated by gulfs that grow wider and more punishing with each step outward. The nearest potentially promising target is the nearest one, and it may not be promising at all. Everything beyond it is worse. Every one of these pressures, social, genetic, physiological, psychological, exists independently of the propulsion problem. Solving the engine does not solve any of them. Building a faster ship reduces transit time, but does not eliminate the radiation environment, the closed society dynamics, the minimum population requirements, or the hardware reliability demands. Making the ship larger to accommodate a viable population increases the mass, which increases the energy requirement, which reintroduces the propulsion problem at a larger scale. The constraints do not queue up politely to be addressed one at a time. They arrive simultaneously, and each one interacts with every other one in ways that compound the difficulty. There is a mathematical argument that makes the situation even worse, and it operates not on the physics of the journey, but on the logic of when to begin it. In 2006, astronomer Andrew Kennedy published a paper examining what he called the weight calculation. The argument is straightforward and devastating. Suppose you launch an interstellar mission today using the best available technology. The ship departs at some velocity, say 5% of the speed of light, and will arrive at Alpha Centauri in approximately 87 years. Now suppose that over the next 50 years, propulsion technology improves, as technology historically tends to do. A ship launched 50 years from now might travel at 20% of the speed of light and arrive in roughly 22 years. That ship, launched half a century later, would arrive at the destination decades before the ship that launched today. This creates a paradox. If you launch now, you will be overtaken. If you wait, you will have a better ship, but you could always wait a little longer for an even better one. The calculation produces an optimal departure date that depends on the assumed rate of technological improvement, and for most reasonable assumptions, that optimal date is always in the future. The logic of the weight calculation says that launching an interstellar mission is never rational in the present because a future mission will always be faster. The only way to escape this trap is if technological progress plateaus, at which point the argument shifts from wait for better technology to this may be the best we will ever have, which is its own kind of defeat. The weight calculation is not a proof that interstellar travel is impossible. It is a proof that the decision to attempt it is irrational under a wide range of assumptions about the future, which means that any civilization capable of doing the math will have a powerful incentive to delay indefinitely. The distance between stars does not merely impose physical costs on the journey, it imposes logical costs on the decision to begin. Now suppose, despite all of this, a mission launches. Suppose it survives the transit. Suppose the crew, or their descendants, arrive at the Alpha Centauri system with their health, their sanity, and their spacecraft intact. What do they find? The Alpha Centauri system contains 3 stars. Alpha Centauri A is a G-type star, slightly larger and brighter than the Sun. Alpha Centauri B is a K-type star, smaller and cooler. The two orbit each other with a period of roughly 79 years at distances ranging from 11 to 36 astronomical units. Proxima Centauri, a dim M-type red dwarf, orbits the central pair at a vast distance of roughly 13,000 astronomical units and is currently the closest individual star to the Sun at 4.24 light-years. Proxima Centauri has at least 2 confirmed planets and 1 candidate. The one that draws the most attention is Proxima Centauri b, discovered in 2016 by the European Southern Observatory. It has a minimum mass of roughly 1.06 Earth masses. It orbits within the habitable zone of its star, the region where surface temperatures could, in principle, permit liquid water. It is, on paper, the closest potentially Earth-like world to our solar system. But the paper description and the physical reality diverge sharply. Proxima Centauri b orbits its star at a distance of approximately 7.5 million kilometers, roughly 20 times closer than Earth orbits the Sun. At that distance, the planet is almost certainly tidally locked, meaning one hemisphere permanently faces the star while the other faces permanently away. The day side would be bathed in constant light. The night side would exist in permanent darkness. The boundary between the two, the terminator zone, might support intermediate conditions, but the climate dynamics of a tidally locked planet are complex and poorly understood. Whether liquid water could exist on the surface depends on atmospheric thickness, composition, and circulation, none of which have been measured. The star itself is the larger problem. Proxima Centauri is a flare star. It regularly produces violent bursts of electromagnetic radiation, including extreme ultraviolet and X-ray emissions, that dwarf anything the Sun produces. These flares are not occasional. They are frequent, with significant flare events occurring on average roughly every 2 hours. The radiation from a single major flare can exceed the quiescent luminosity of the star by a factor of several hundred in the extreme ultraviolet. At the orbital distance of Proxima Centauri b, these flares deliver surface radiation doses that would be sterilizing for unprotected biology. NASA models have estimated that the extreme ultraviolet flux at Proxima b's orbit is hundreds of times greater than what Earth receives from the Sun. Over geological timescales, this radiation is expected to strip atmospheric gases away from the planet, particularly lighter elements like hydrogen. Whether Proxima b retains any atmosphere at all remains unknown. If it does not, the surface is directly exposed to the stellar wind and cosmic ray environment with no protection, making it less a habitable world and more an irradiated rock, baking under constant flare bombardment on one side and frozen in permanent darkness on the other. This is the nearest potentially habitable planet, the closest place in the universe where another world orbits at the right distance from its star for liquid water to theoretically exist on its surface. And the best current evidence suggests it may be a tidally locked, atmosphere-stripped, radiation-blasted body orbiting a violent and unstable star. It might not be habitable at all. The journey to reach it would take decades at minimum, would require solving every engineering, biological, and social challenge described in this story. And the reward at the end might be a destination that cannot support human life. In 2025, the James Webb Space Telescope provided the strongest evidence yet for a candidate gas giant orbiting Alpha Centauri A within that star's habitable zone. Follow-up observations in February and April of 2025 did not redetect the object, leading researchers to propose that it may have an elliptical orbit, carrying it in and out of the detection zone. Additional observations are planned for August 2026. If confirmed, it would be a gas giant, not a rocky world, and gas giants do not support surface life as we understand it, though their moons are a separate question that remains entirely unanswered for this system. The point is not that the Alpha Centauri system is definitively lifeless or useless. The point is that the nearest star system, the one that costs the least to reach, the one that requires the smallest miracle of engineering, may not offer what the journey demands in return. The cruelty of the interstellar distance is not only in the crossing, It is in the possibility that what waits on the other side does not justify the price of getting there. And before any of this is reached, before a spacecraft even enters the Alpha Centauri system, it must first leave our own. That departure takes longer than most people imagine, because the solar system does not end where the textbooks draw the line. The outermost major planet, Neptune, orbits at roughly 30 astronomical units from the Sun. The Kuiper Belt extends from roughly 30 to 50 astronomical units, a disk of icy bodies including Pluto, Eris, and thousands of smaller objects. Beyond the Kuiper Belt lies the scattered disk, a more diffuse population of icy bodies with orbits that extend to hundreds of astronomical units. And beyond the scattered disk, beginning at roughly 2,000 astronomical units and extending outward to perhaps 100,000 astronomical units, sits the Oort cloud. The Oort cloud is a theoretical shell of icy objects surrounding the solar system, gravitationally bound to the Sun but so loosely that perturbations from passing stars and the galactic tide can dislodge them and send them falling inward as long-period comets. It has never been directly observed. Its existence is inferred from the orbits of comets that arrive from all directions, suggesting a roughly spherical source region at enormous distance. If the Oort cloud extends to 100,000 astronomical units, its outer edge is approximately 1.6 light-years from the Sun. Alpha Centauri is 4.37 light-years away. That means the Oort cloud occupies roughly a third of the distance between the Sun and the nearest star. A spacecraft departing Earth would spend years or decades crossing through a region still gravitationally bound to the Sun before it even entered true interstellar space. The boundary of our solar system is not a clean line. It is a gradual fade, a slow dissolving of the Sun's influence that stretches across trillions of kilometers. This is the physical reality that the night sky conceals. When you look at the stars and see them as destinations, your mind skips over the approach, the crossing, the arrival, the conditions at the other end, and the return. It treats the journey as a line drawn between two dots on a chart. The actual journey is not a line, it is a gauntlet. Leaving the solar system takes years, crossing the void takes decades. Arriving at the destination delivers you to a system that may or may not offer what you need. And returning, if return is even contemplated, doubles the entire ordeal. There is one more element of the compounding cruelty that deserves to be named before we reach the final reckoning. It is the problem of institutional memory. Every crewed interstellar mission assumes that the civilization that launches it will still exist when the mission concludes. The spacecraft needs a destination to report back to. The crew needs a reason to believe their sacrifice will be received, recorded, and valued by the culture that sent them. But the transit times involved in interstellar travel exceed the lifespan of most human institutions. The Roman Republic lasted roughly 5 centuries. The British Empire lasted roughly 3. The United States has existed for 2.5. The longest-lived human institutions, certain religious organizations, and a handful of universities have histories stretching back roughly 1,000 years. An interstellar mission lasting several centuries would outlast every institution currently operating on Earth. The civilization that launched the mission might not recognize itself by the time the mission concludes. The world the crew left behind will not remain frozen in the state they remember. It will keep moving, keep changing, keep becoming something new, indifferent to the promises made on the launch pad. But there is a subtler version of this problem that does not require civilizational collapse. It requires only change. Normal, expected, inevitable change. And it may be more corrosive to the purpose of the mission than any catastrophe. Consider what happens on Earth during the decades or centuries of transit. Technology does not stand still. The propulsion systems available at the time of launch will be superseded by newer, more capable designs. The scientific instruments the crew carries will be obsolete long before they arrive. The questions the mission was designed to answer may have already been answered by telescopes, by robotic probes launched on faster trajectories after the crewed mission departed, or by theoretical breakthroughs that rendered the original observations unnecessary. The crew travels for half a century to gather data that Earth may already possess by the time they arrive at the destination. They are not exploring. They are reenacting an exploration that has already been completed by faster means. Language drifts. English, as spoken in 2026, is meaningfully different from English as spoken in 1926, and the gap widens the further back you go. A crew that departs, speaking the language of their era, will, after a century of isolation, develop their own dialect, shaped by the closed environment of the ship and cut off from the linguistic evolution occurring on Earth. The messages they send home may become progressively harder for Earth-based recipients to pass. The cultural references they carry will become historical artifacts. The music, the literature, the shared assumptions about society and meaning that bonded the crew to their origin culture will ossify aboard the ship while the living culture on Earth continues to evolve. The travelers become, in a very real sense, foreigners to their own species. Purpose drifts too. The political consensus that funded the mission may dissolve within a single election cycle, let alone across decades. The institutions that championed the launch may be restructured, defunded, or absorbed into larger entities with different priorities. A mission launched with enormous public enthusiasm may arrive to find that no one remembers why it was sent. The crew's sacrifices, the years of confinement, the radiation exposure, the psychological toll may be met not with celebration but with indifference, or worse, with the quiet embarrassment of a civilization that has moved on and no longer recognizes itself in the ambitions of its ancestors. The cruelest version of this outcome is not that the mission fails. It is that the mission succeeds and no one cares. The data arrives, and the civilization that receives it has already obtained better data by other means, from instruments that did not require human suffering to operate. This is not a failure of planning. It is a structural feature of the timescales involved. Interstellar distance does not merely exceed the range of our engines or the endurance of our bodies. It exceeds the lifespan of our civilizations. It asks us to commit to projects that stretch across more time than any human organization has ever survived, and it offers no guarantee that anyone will be listening when the project is complete. The distance between stars compounds every cost. It multiplies every risk. It extends every timeline past the breaking point of every system involved, from the mechanical to the biological to the social to the institutional. It does not challenge exploration the way that crossing an ocean challenges exploration, with a finite set of obstacles that can be overcome through courage and preparation. It challenges exploration by stacking an open-ended series of obstacles so deep that solving the first layer exposes the second, and solving the second exposes the third, and the third is worse than the first two combined. What this means, what the full weight of this compounding cruelty implies about the stars and our place among them, is the question that remains. And answering it requires looking not at the engineering, but at the architecture of the universe itself, at why the stars are spaced the way they are, at what that spacing might mean for every civilization that has ever looked up, and at the possibility that the distance between stars is not merely an obstacle on the road to the future, but the first wall that the universe builds around every species that learns to dream of leaving home. There is a question that lives underneath everything we have discussed so far, and it is time to let it surface. We have talked about engines and fuel. We have talked about radiation and shielding. We have talked about communication delays measured in years, about hardware that must function for decades without repair, about closed societies that must hold together across generations, about destinations that may not be worth the price of reaching them. Every one of those problems is real. Every one of them has been studied, modeled, debated, and published in peer-reviewed literature. But underneath all of them, quiet and rarely spoken aloud, is a deeper question that the engineering cannot answer. What if the distance between stars is not a problem to be solved, but a condition to be understood? What if it is not an obstacle on the road to an interstellar future, but the shape of the road itself, and the shape says no? This is not a comfortable question. Humanity has spent its entire conscious history treating barriers as temporary. The ocean was a barrier until we built ships. The sky was a barrier until we built aircraft. The vacuum of space was a barrier until we built rockets. Each time, the pattern held. The barrier looked permanent, and then it fell. The instinct to project this pattern forward, to assume that interstellar distance will eventually yield to some future technology the way every previous distance yielded, is not irrational. It is deeply human. It is also, for the first time in the history of exploration, potentially wrong. The reason it may be wrong has nothing to do with imagination or ambition. It has to do with the structure of the problem. Every previous barrier that humanity overcame shared a set of features that made it, in retrospect, solvable. The ocean was wide, but it was made of water, and water supports boats. The atmosphere was thin, but it was made of gas, and gas supports wings. Low Earth orbit was high, but it was close, and the energy required to reach it, while enormous by the standards of everyday life, was finite and achievable with chemical reactions. Each barrier presented a single dominant challenge that, once addressed, made the rest of the journey tractable. Build a boat strong enough to survive the waves, and the ocean becomes crossable. Build an engine powerful enough to sustain flight, and the sky becomes accessible. Build a rocket powerful enough to reach orbital velocity, and space becomes reachable. The distance between stars does not work this way. It does not present a single dominant challenge. It presents a matrix of challenges, interconnected and mutually reinforcing, where solving one shifts the burden to another without reducing the total difficulty. This is a structurally different kind of problem from anything humanity has previously encountered in exploration, and it is the reason that historical analogies about ocean crossings and first flights may not apply. The person who says we will cross the interstellar gulf the same way we cross the Atlantic is making an argument by analogy, and the analogy breaks down precisely at the point where it matters most. The Atlantic was wide. The interstellar gulf is wide and radiative and empty, and long enough to outlast the machinery, the biology, and the institutions of any traveler. The width was the only problem with the Atlantic. The width is just the beginning of the problem with interstellar space. Consider what it would mean if this is true. Not proven, not certain, but true as a working description of the situation as we currently understand it. It would mean that the universe has a structure in which stars are separated by distances that biological civilizations cannot practically cross. Not cannot in the absolute sense that physics forbids it. Light can cross the distance, signals can cross it, perhaps even tiny robotic probes, if the engineering challenges are eventually solved, can cross it. But biological civilizations, societies of living beings with finite lifespans, social needs, institutional fragilities, and physical vulnerabilities, may not be able to cross it in any way that preserves them as what they were when they started. A crew that departs Earth and arrives at Alpha Centauri 50 years later is not the same crew. A generational ship that departs Earth and arrives 200 years later carries people who have never seen Earth and who may not meaningfully identify with the civilization that launched them. A society that sends its members on a one-way journey, measured in lifetimes, is not exploring, it is dispersing. And dispersal across distances that prevent communication, prevent rescue, prevent cultural continuity, and prevent any form of feedback between the colony and the origin is something qualitatively different from every act of exploration that came before it. This distinction matters because it changes what the silence of the cosmos might mean. The Fermi paradox asks why, in a galaxy billions of years old and hundreds of billions of stars wide, we see no evidence of other civilizations. Dozens of explanations have been proposed. They self-destruct with nuclear weapons. They are hiding. They transcend into digital existence. They are sleeping. They were never there. Each of these explanations assumes that if a civilization survives long enough and develops sufficient technology, it should be able to expand across the galaxy. The distance between stars is treated as a speed bump, something that slows expansion but does not prevent it. But what if the distance between stars is not a speed bump? What if it is a wall? Not a wall in the dramatic sense of some cosmic barrier made of exotic matter. A wall in the quiet, structural sense that the distances involved degrade every mechanism of expansion below the threshold of viability. Engines cannot carry enough fuel. Crews cannot survive long enough. Societies cannot maintain coherence. Institutions cannot persist across the required timescales. Communication cannot bridge the gap in time to matter. Rescue cannot arrive in time to help. Every thread that connects a traveler to a civilization frays and snaps somewhere in the crossing, and without those threads, the traveler is no longer an explorer, but a castaway. If this is the case, then the Fermi paradox does not require a great filter. It does not require self-destruction, or transcendence, or predatory alien empires enforcing silence. It requires only the geometry of the galaxy. Stars are spaced far enough apart that biological civilizations cannot meaningfully bridge the gaps between them. Each civilization that arises does so on its own world, in its own system, and remains there. Not because it lacks ambition or intelligence, but because the universe placed its stars at intervals that make expansion physically impractical. The galaxy is not empty because civilizations destroy themselves. It may be quiet because every civilization that has ever existed is sitting on its home world, looking up at the same stars we see, running the same calculations we run, and arriving at the same conclusion. The gulf is too wide. The crossing is too long. The destination is too uncertain. The cost is too total. There is something deeply unsettling about this possibility, and the source of the unease is worth examining because it reveals something about the human relationship with the stars that goes beyond science. The stars have never been merely astronomical objects to human cultures. They have been destinations, promises, evidence of a universe that extends beyond the horizon and therefore extends the possibilities of life beyond the horizon. Every mythology that includes the stars treats them as places. The Greeks put their heroes among them. The Polynesians navigated by them. The science fiction of the 20th century, arguably the dominant mythology of the technological age, built its entire vision of the future around the assumption that the stars were reachable. Warp drives, hyperspace, jump gates. Faster-than-light travel in some form was not just a plot convenience. It was the foundational assumption of a civilization that believed its destiny lay among the stars. What the physics actually says is different. The speed of light is not a speed limit in the way that a highway speed limit is a speed limit, an arbitrary rule imposed by an authority and enforceable by penalty. It is a structural feature of space-time itself. Nothing that carries information or has mass can exceed it. This has been confirmed by every experiment in the history of physics. There are no known exceptions. There are no credible theoretical frameworks that offer a way around it without invoking exotic matter that has never been observed and may not exist. The speed of light is not a barrier waiting to be broken. It is a description of how the universe is built. And the speed of light, which feels like it should be fast enough for anything, is agonizingly slow on the scale of the galaxy. Light takes 4 years to reach the nearest star. It takes 100,000 years to cross the Milky Way. It takes 2.5 million years to reach Andromeda. The universe is built on a scale where even the fastest possible speed is not fast enough to make travel between stars feel like travel. It feels like exile. This is the emotional core of the cruelest distance. The stars are visible. They are beautiful. They are scientifically fascinating. We can study their spectra, measure their masses, detect their planets, and even characterize the atmospheres of some of those planets from 4 light-years away. We are not ignorant of them. We are intimate with them in every way, except the one that matters to a species built for exploration. We cannot go there. We can look. We can listen. We can calculate and model and simulate. But we cannot walk on those worlds, breathe that air, touch that soil, or stand beneath that alien sky. The universe gave us eyes sharp enough to see the destination and legs too short to reach it. Some will argue that this framing is too pessimistic, that technology has always surprised us, that the history of forecasting is littered with confident declarations of impossibility that later turned out to be wrong. Lord Kelvin said heavier-than-air flight was impossible. The head of IBM said the world market for computers was maybe 5. These examples are usually deployed to suggest that anyone who doubts the feasibility of interstellar travel is making the same mistake, underestimating human ingenuity. But there is a crucial difference between those historical examples and this one. Kelvin was wrong about flight because he underestimated the engineering, not because he misunderstood the physics. The physics of lift, drag, and thrust were well understood. The engineering challenge was to build a machine light enough and powerful enough to exploit them. The physics of interstellar travel is also well understood, and it is the physics, not the engineering, that creates the fundamental constraint. The speed of light is not an engineering challenge. It is a law of nature. The energy requirements for relativistic travel are not an engineering challenge. They are a consequence of mass energy equivalence. The radiation environment of interstellar space is not an engineering challenge. It is a consequence of living in a galaxy filled with high-energy particles. Engineering can mitigate these constraints. It cannot remove them. And the constraints, even after mitigation, remain severe enough to make crude interstellar travel a proposition of a fundamentally different character from any journey that preceded it. It is possible that post-biological intelligence could change the calculation. An artificial mind does not suffer from radiation-induced cancer. It does not experience psychological distress from decades of confinement. It does not need food, water, or breathable air. It does not have a finite lifespan that the transit time must fit within. A machine intelligence, sufficiently advanced and sufficiently compact, could, in principle, endure a journey that no biological crew could survive. It could be launched on a slower trajectory, taking centuries or millennia to cross the Gulf and arrive functionally intact. It could explore the destination, analyze its findings, and transmit the results back to Earth at the speed of light. This is a genuine possibility, and perhaps the most realistic path to gathering information from another star system. But notice what it does not do. It does not carry humanity to the stars. It carries a machine. The human beings who built it remain on Earth, separated from the destination by the same unbridgeable gulf. They receive data. They do not receive experience. They do not set foot on another world. They do not breathe alien air. They do not feel the gravity of a planet that orbits a different sun. The machine goes, the people stay, and the distance between here and there remains exactly what it was. Even the machine faces versions of the same constraints that afflict a crewed mission, though in diminished form. It still needs energy. It still needs shielding. Its hardware still degrades over time, and a journey lasting centuries imposes reliability requirements that far exceed anything in current engineering experience. It still cannot communicate with Earth in real time. A command sent to a robotic probe at Alpha Centauri takes 4.37 years to arrive. The response takes the same. The probe must operate autonomously for the entire mission, making every decision without guidance, because guidance is functionally impossible across interstellar distance. If the probe encounters something unexpected, something that requires a decision outside its programming, it must either handle the situation on its own or fail. There is no operator on the other end of the link who can take over the controls. Some researchers have suggested that the galaxy might eventually be explored not by individual missions, but by self-replicating probes, machines that land on asteroids or moons in a target system, mine raw materials, build copies of themselves, and launch those copies toward the next star. The mathematics of exponential replication suggest that such a process, once initiated, could fill the galaxy with probes in a few million years. The concept is theoretically sound. It is also the strongest argument against the idea that the galaxy is filled with other civilizations, because if any civilization had ever built and launched a single self-replicating probe at any point in the last several billion years, the galaxy should already be saturated with their descendants. We see no such probes. Either no civilization has ever built one, or there is something about the interstellar environment that prevents the process from working as the mathematics predict. Perhaps the machines break down faster than they can replicate. Perhaps the resources at each stop are insufficient. Perhaps the distances between stars impose a minimum transit time that, multiplied across thousands of hops, stretches the process past the operational lifetime of the machines. The galaxy may be structured in a way that resists even robotic exploration at scale. What remains, after all the engineering is exhausted and all the alternatives are explored, is the distance itself. 41 trillion kilometers to the nearest star. 4.37 years at the speed of light. 73,000 years at the speed of Voyager. It sits there, patient and immovable, between every star and every other star in the galaxy. It does not negotiate. It does not yield to ambition or urgency or need. It is not malicious. It has no intent. It is simply the way the universe is built, the spacing between the fires that burn in the dark, and that spacing happens to be large enough to isolate every civilization that arises on every world, around every star, from every other one. The cruelest distance in space is not the diameter of the observable universe. That distance is so vast that it passes beyond cruelty into pure abstraction. No one grieves for the inability to reach a galaxy 10 billion light-years away. The cruelest distance is not the span between galaxy clusters or the width of the cosmic voids. Those distances are irrelevant to any practical consideration and therefore carry no emotional weight. The cruelest distance is the one between stars. It is cruel because it is the first distance that breaks the pattern. Every distance smaller than it has been crossed or can be credibly imagined being crossed. The moon is 3 days away. Mars is months away. The outer planets are years away. These are hard destinations, but they are destinations reachable within a human lifetime, within a single career, within the span of a civilization's attention. The distance to the nearest star is the first distance that exceeds all of those limits simultaneously. It is the first distance that cannot be crossed within a human lifetime using any technology that currently exists or is under credible development. It is the first distance that breaks communication, eliminates rescue, outlasts institutions, and degrades biology. It is the first distance where the word mission loses its meaning, where exploration becomes something closer to exile, and where the relationship between a traveler and home dissolves completely during the crossing. It is cruel because of where it falls. It falls right at the edge of our reach, close enough to tantalize and far enough to defeat. If the nearest star were 100 light-years away, the question would not haunt us because the impossibility would be too obvious to inspire hope. If it were 1/10 of a light-year away, the challenge would be severe but probably surmountable within a few generations of engineering progress. But 4.37 light-years is the worst possible distance for a species like ours. It is close enough that we can see worlds orbiting there, close enough to name them and study them and wonder about them, close enough that a physicist can sketch a propulsion system on a whiteboard and say, in theory, this could work, and far enough that every attempt to turn that theory into reality runs into a wall of compounding constraints that no one has found a way through. Tonight, when the sun sets and the sky clears, you will see the stars. If you are in the southern hemisphere, you will see Alpha Centauri, a bright point of light hanging among thousands of others, looking no different from the rest, looking close. Your brain will do what it has always done. It will place the stars within reach. It will treat them as destinations, as the next horizon, as the place where the future lives. This is not a failure of your imagination. It is its greatest strength and its deepest deception, because the stars are not the next horizon. The next horizon is Mars, the asteroids, the moons of Jupiter and Saturn. The stars are something else. They are the place where the horizon ends, not metaphorically, physically. The space between them is wide enough, empty enough, hostile enough, and long enough to function as a boundary, the first boundary the universe imposes on the ambitions of any species that learns to leave its home world. The universe is not small, it is not closed, it is not barren. There are trillions of stars in the observable cosmos, and orbiting many of them are worlds of stone and water and gas, worlds that may harbor chemistries we have never imagined and landscapes we have never seen. All of it is out there, all of it is real, and between every one of those worlds and every other one, the gulf yawns, silent, cold, and impossibly wide. The cruelest distance in space is not the farthest one. It is the nearest one that you cannot cross, and it begins just past the edge of the solar system, in the 4 quiet light-years between one ordinary star and the next, where the dreams of every civilization that has ever looked up at the night sky go to meet the universe as it actually is. The stars are beautiful. They always have been. And they are farther away than you feel, farther than your instincts believe, farther than the stories have prepared you for. The distance between them is the first great silence of the cosmos, and we are sitting inside it, listening for a voice that may never come, because every other world that might have sent one is sitting inside the same silence, separated from us by the same impossible, patient, unforgiving dark.